So this talk is on efficient management of temporary data and data processing workloads. So let's start by talking about temporary data a little bit in the first set of minutes. So data processing frameworks like Spark, Flink, Hadoop, they have to deal with different types of temporary data. And with temporary data, we mean data that has a limited lifetime. Examples of such data are broadcast data in Spark, shuffle data in Spark, RDD caching, or any other similar data set in other frameworks. We say broadcast and shuffle are examples of intra-job temporary data because the lifetime of that data is bound to the lifetime of a job. There is also inter-job temporary data, which like intermediate results shared between jobs in more complex workflows. Think about a machine learning workflow where your training phase is operating on pre-processed data that has been computed by a MapReduce job. That pre-processed data, just like shuffle data or broadcast data, has a limited lifetime bound to the duration of the workflow in this case. So it turns out that temporary data is in fact an important class of data. 97% of all queries in the TPCDS benchmark, when run on Spark, have at least one broadcast or shuffle operation. Rifle, a recent paper from Facebook on optimizing shuffle performance, reports that 50% of all jobs at Facebook have at least one shuffle operation. And similarly with machine learning workloads, many machine learning workloads actually consist of multiple jobs sharing data between jobs, and there are several frameworks to manage those kind of workloads. So what's the problem with temporary data, or how temporary data is being managed? There's actually two issues I want to talk about. The first issue is related to performance. Turns out that it's very difficult to leverage fast networking and storage hardware, particularly for shuffle and broadcast operations. This figure shows, gives you an idea how bad the situation is. So this is showing the throughput on the y-axis and the runtime on the x-axis of a terasort a sorting workload in Spark on a 100 gigabit cluster, so a cluster with a 100 gigabit Ethernet network. In this case, the data set is entirely in DRM, so we're not hitting disk at any point in time. And as you can see, the bandwidth is never going above 5 to 10 gigabits per second. That's unfortunate because sorting is actually one of the most I/O-intensive workloads you can think of. The entire input data set literally has to be shuffled over the network at least once, so it would be fantastic if we could make better use of the network here in this case. Now, these type of performance issues, this is related to shuffle here. Similar performance issues have been shown for other types of temporary data, and there are papers from the past that basically document these kind of performance issues. Now, let's talk about the second issue, which is related more to the software architecture of these systems. Turns out that assume you want to address those performance issues because you may have an idea how to integrate networking in a sort of in a better way within your shuffle or broadcast operations. That's going to be painful to do because temporary data management is often tightly integrated with the compute framework. So you would have to go and rework your shuffle module, your broadcast module, the way RDD caching is implemented. And by the time you get all these modules work efficiently on a 100 gigabit network, you find out that they're not using Flash effectively. And maybe you find out that they don't support storage disaggregation well, right? So you would have again to go and look at each of these modules. And once you've done that, you still have only looked at one framework, but maybe your workflow consists of multiple jobs running in different frameworks, right? So clearly we don't want to modify the shuffle, broadcast modules, all these different modules for the different frameworks each time we want to support a new hardware or a new deployment mode. In this work, we argue that a more flexible approach to deal with this is to separate, at least logically, data processing from temporary data management. Instead of directly exchanging data between tasks, which is what current implementations for broadcast and shuffle are doing, data sharing should be implemented as storage operations on top of an external distributed data store. And by doing so, supporting new hardware or new deployment modes becomes much more easy, right? Now, if your data store is running efficiently on a 100 gigabit network, your shuffle implementation will immediately pick it up. If your data store is able to run in a disaggregated environment, your shuffle operation will be able to run in a disaggregated environment. Now, obviously the next question is, how should that data store look like? Can we use any of the existing distributed storage platforms like a distributed key value store or a distributed file system? And so we set out to kind of better understand the requirements of temporary data storage by looking at the size distribution of temporary data for different workloads. This graph here shows the amount of broadcast and shuffle data generated per task for a TPCDS workload, a PageRank workload on the Twitter graph, and the machine learning workload on the Cocoa framework, all of this executed on a Spark cluster. And the main observation here is that the data range is a quite wide range of data. So it starts from a few kilobytes all the way up to 1 gigabyte. And what does that mean in terms of data storage, Over the last years, the research community has come up with some really good high-performance storage platforms covering both ends of this spectrum, like RAM Cloud, Pilaf. I haven't mentioned Pilaf here, but are examples of low latency key value stores, RDMA based, giving you really good performance for small data sets, right? Octopus is an example of a recent example of a file system that is also RDMA based, running on Flash, giving you high bandwidth access to large data sets. But it turns out that finding a storage platform that is able to operate well across the full spectrum, offering high performance for any size of data, is a much harder problem, right? Many storage platforms either don't support arbitrary data sizes, or they are not performing well for the entire spectrum. And often the limitations are actually by design. In a distributed, as a key value pair in a distributed key value store is always stored on one server, limiting the access bandwidth to that key value pair if the data gets really large. On the other hand, file systems just typically cannot meet the latency, cannot match the latency of key value stores due to additional metadata operations. So the need to perform well for a wide range of data sizes put us on new ground where we were saying, okay, let's build something new, right? And once we are about to build something new, let's ask ourselves what other requirements we need to fulfill. Well, first, we need to support large volumes of data. Shuffle data can be as large as the input data, so clearly a purely in-memory based approach is not cost effective. We also need to think about the abstractions we want to provide to the data processing framework, right? A key value interface might be a good abstraction for storing broadcast objects. A file system streaming bytes-based abstraction might be a good match for caching input data sets, fetched from HDFS or so. But neither a key value or a file system abstraction might be a good match for shuffle data, which is written randomly and read sequentially, right? We also need scalability. At least we need to be as scalable as the data processing framework, probably more scalable because we want to share the storage platform across multiple jobs. There are also requirements that may require less attention in a temporary data storage system, like fault tolerance or durability, right? So temporary data is often stored only for a short amount of time, and data processing frameworks often have fault tolerance baked in a sense that they can recompute data if it's being lost. So maybe replicating each data item 3 times is an overkill. That doesn't mean we don't need fault tolerance. At the end of the day, it's a trade-off between, or it depends on the likelihood of losing data, and it's a trade-off between the cost of adding fault tolerance versus the cost of recomputing data. So based on these requirements, we've designed NodeKernel, which is a new storage architecture for temporary data. At the high level, NodeKernel fuses file system semantics with key value semantics to give you the best of both worlds, if you want. So it's going to work well for small data sets. It's going to give you low latency for small data sets, and it's going to work well for large data sets as well, giving you high bandwidth access to large data sets. NodeKernel is designed with modern hardware in mind, so many of the design decisions in NodeKernel are actually direct consequences from some of the characteristics in fast network and storage hardware. So let's dive into the data model of NodeKernel. So NodeKernel exposes a hierarchical namespace of nodes. Applications can create new nodes, look up nodes, rename nodes, delete nodes, and so on. But and the hierarchical namespace is convenient because it allows applications to separate different types of temporary data, and also separate logically data from different jobs within a single storage namespace. Now, unlike a file system, for instance, where the data is entirely stored in files, data in the node kernel can be attached to any node. So NodeKernel defines a type node where that has operations to append data to a node, to update data that has been written already, and to read data that has been written. Now, NodeKernel also defines several specific node types. These node types are tailored to particular types of temporary data and offer special functionality to support that. So, for instance, there is a directory and a file node type, right? The directory has an additional operation to enumerate all of its children. So directories and files are a good abstraction to for instance, for caching of input data sets. There is also a table and a key value node abstraction. A table has put-get operations to insert a new key value node into the system or to atomically replace an already existing key value node. And those table abstractions are helpful to organize or to store data that has regular updates. And then there is also a bag abstraction that goes in concert with the file abstraction. A bag is basically a flat directory of files, but it has an additional operation to read the full content of all of its files within the bag as if the bag was a single large file. And the bag abstraction, as we'll see later, is very helpful in a shuffle operation because we can actually map each partition in a shuffle operation to one bag. Now, let's take a look how data is stored in the NodeKernel architecture. And the system architecture, this is a typo here. I see. This is should be NodeKernel. Crail is actually our implementation of the architecture. We'll get to that in a moment. But so the system architecture is actually not much different than the system architecture of, let's say, a distributed file system or like HDFS or GFS. So data is chopped up into blocks, and the blocks are distributed across multiple storage servers. One difference in NodeKernel is that the storage servers are logically grouped together into so-called storage classes. And the simplest way to think about a storage class is that it is containing all the storage servers that store blocks of a particular type. So you might have a storage class for DRAM consisting of all storage servers storing blocks in DRAM, and then you may have a storage class for Flash consisting of all storage servers storing blocks in Flash. Now the decision about which storage class to use for a node and how to distribute the blocks across the storage servers, those decisions are made by the metadata servers in the system. And the metadata servers, they maintain a pool of free blocks, and when the application is appending data to a node, the metadata server has to decide which block to take out of the free list of which storage class to store that particular data. And in the NodeKernel architecture, we're advocating a policy called hierarchical tiering, which means that the storage server will always try to allocate a block from the fastest performing tier. It means that it will only allocate a Flash block if there is no block in DRAM available across the entire cluster. You may have also observed that the metadata plane consists of multiple metadata servers. The reason for that is that we partitioned the storage namespace across multiple metadata servers by hash partitioning it. So each of the metadata servers is responsible for one subtree in the storage namespace. Given that architecture with a metadata plane and a data plane, almost every of these data operations to append or read or update data require two operations, one involving the metadata server to find out which storage server has the block, and one operation to actually read or write the block. And this message flow is illustrated by this figure for the example of appending data to a key value node. And the point of that figure is to show that the fact that in NodeKernel we're using an additional metadata plane, that gives us extra flexibility because in every operation we can literally, the metadata server can decide what is the best storage server to store that block, what is the best storage tier to store that block. But clearly that is going to cost us extra round trips. And this, in the case of a key value node put operation, this is going to be 2 extra round trips because in the end we also have to inform the metadata server about the new size. So those 2 extra round trips are 2 round trips more than what you would get in a normal, let's say, distributed key value store doing a put. And the line of thought in NodeKernel is that with current and upcoming networking, low latency networking fabrics, we can minimize the overhead of such a metadata operation to a few microseconds. And this is what gets us to Crail. Crail is our implementation of the NodeKernel architecture. It's using low latency RDMA-based RPC to minimize those metadata, the overhead of those metadata operations. Crail is coming with 2 storage classes, one exporting flash that is being accessed over NVMe over fabrics. There's not going to be enough time to talk about NVMe over fabrics here, but think of it as a really fast way to access remote flash over RDMA. And the second storage class is exposing DRAM that is accessed over RDMA read-write operations. And Crail is open source and is an Apache project, incubator project since the beginning of last year. Now let's look at how this performs. This is an evaluation on 16 nodes on a 100 gig network. The nodes have 256 gigabyte of DRAM, some Intel Optane SSDs in there. And the main question we try to answer is, first, is Crail really giving you good performance for the full spectrum? We said we need the system to perform well for small and large values. Is it allowing you to translate, accelerate workloads by using modern hardware effectively? How are the abstractions of Crail? Are they flexible enough so we can build let's say, shuffle engine easily on top of it? And can we easily play around with Crail in a way that it gives us flexibility? Can we enable storage disaggregation, flash tiering easily without having to go and modify the higher level modules? So this figure here is showing you on the left side the performance of Crail for small value get operations. So this is this involves the full message flow I've shown before, including a metadata operation and a read operation to get the 256 bytes out of a storage server. And we show this for both the DRAM tier and the SSD tier. And you can see we are getting down to values that are very close to the hardware limits. So the DRAM latency here is a little bit above 10 microseconds. So that's reasonably low. On an RDMA link, you can maybe access remote DRAM in like 3 microseconds. And for the Optane tier, we are a little bit higher than 20 microseconds, and the raw access to a remote Optane is about 15 microseconds. And you can see we're getting quite stable latencies up to a point where we're hitting either the hardware limit or the limit of a single metadata server in Crail. So for the DRAM case, we are hitting 8 million IOPS, which is the limit of a single metadata server in Crail. And for the optamp benchmark, we are hitting the limit of the device at a slightly lower value. On the right-hand side, you see a similar benchmark for a large data set, where we are looking at the throughput of reading that data set. And again, you can see that for DRAM, we're getting close to 100 gigabits per second read bandwidth very quickly for small I/O sizes. And for Flash, it takes a little bit higher I/O sizes to get the reasonably good throughput, and we're not getting all the way to line speed. But it's still a fairly good performance. Now that we have seen that Crail can give you reasonably good performance across the full spectrum, let's see whether the abstractions we design in Crail are helpful and allow us to build, let's say, higher level operations effectively. This is a shuffle, the basic architecture of a shuffle operation in Spark. I assume many of you guys are familiar roughly what a shuffle operation is doing and how it is working. So the map tasks, they are getting data and they are partitioning the data into multiple buckets, shown with multiple colors in this case. And then once the map phase is finished, the reduce phase consists of a set of reduce tasks where each reduce task is assigned to one bucket and is fetching all the data of that bucket. Using the Crail bag abstraction, we can model such a shuffle operation easily by having the map task, by assigning a partition to one bag, right? And then each map task is partitioning its data into a set of files, one file per bag, right? One file per partition. And once the map task is finished, the reduce tasks simply read the entire bag for that particular partition they are assigned to. And this is showing how this performs on a 100 gigabit network compared to the default shuffle engine in Spark. So this is a group by benchmark, which is stressing the shuffle engine. It's a group by on 8 million keys, 4K size per key. And you can see that the figure shows the performance for different numbers of cores. So you can see we're about 5 times faster with the Crail-based shuffle engine with a single core than the vanilla Spark shuffler. And even if you're throwing 8 cores on the vanilla Spark shuffler, we are still about 2 times faster with a single core. So this performance translates to either better performance or better efficiency, as in less cores. Now, the last figure I want to show is that one value proposition of this architecture, right? We said we want to decouple temporary data management from data processing. So one value proposition from this architecture is that you can change your configuration in Crail, and it will immediately be picked up by the higher level operations. So you can, for instance, play around with the DRAM flash ratio, or you can deploy Crail as a disaggregated storage platform, and immediately that will be picked up by your shuffle operation. And this is an example that shows the value of Crail and the flexibility of Crail by changing the ratio between DRAM and flash. So we are changing the ratio between DRAM and flash. We export in Crail from initially 100 to 0 means the entire Crail deployment is DRAM based. And 0 to 100 means the entire deployment is flash based. And on the very left, you see the performance of vanilla Spark sorting benchmark. We are sorting 200 gigabytes in this case. Right. So 2 things that this figure is showing. First of all, we are substantially faster, independent of whether we're using DRAM or flash. And the second is we can easily adjust the ratio between flash and DRAM, and thereby trade off performance for cost. So by putting in all flash instead of DRAM, we're paying about 48% penalty, but we can reduce the cost substantially. So that's basically the end of the technical part. The conclusions is that sharing temporary data efficiently in data processing frameworks is challenging. challenging because it's difficult to implement it efficiently and flexible in a flexible manner so that you can support new hardware, new deployment modes. And NodeKernel is a distributed storage architecture that is designed for temporary storage. It's fusing file system and key value semantics into a single store, and it's designed for modern hardware. And Apache Crail is our current implementation of this architecture. It's open source. It's using RDMA and NVMe to access DRAM and Flash, and is able to accelerate Spark workloads and other workloads that are shown in the paper. I also want to point out that all the code is open source. The storage system, of course, the shuffle engine is open source as well. And in the paper, we have also YCSB benchmarks, benchmark numbers, and the YCSB benchmark is actually officially part of the YCSB benchmark suite since a month. So with that, yeah, I'm happy to take questions.
We have time for one question.
Peter Matsko from NetApp. Question. So you said you have a single namespace about the different types. So, but do you by any chance provide like a dual access? Like, can you use a KV API or N-file API on the same on the same name, or?
So, a single node in that namespace is always bound to a particular type. So, I have a maybe I can show this example here. I don't know if you can read this well, but this is showing the API in Crail. So when you create a new node in the storage hierarchy, the nodes are identified with path names, and you have to specify a type when you create a new node. So at the creation time, you decide what type of node you want to create, and then that node is basically is fixed for the rest of your usage.
Thank you.
Chu Yonghwang from Samsung Electronics. So thank you for great talks. I'm curious why you use the Optane SSD rather than a normal TLC or QLC SSD.
So we use both, and the paper has numbers for both. For this talk, there was just not enough time to cover all those benchmarks, but we use both, and I've selected the Optane numbers for this talk.
So what do you think about the performance requirement? Do you still need a kind of NVM style latency or just a normal flash latency?
I mean, Crail is not necessarily making any statement about this. So the basic idea is that different types of technologies are out there, and we build a system that allows you to integrate these different technologies. And one way you can integrate it into Crail is through different storage classes. So if you have different types of, if you have flash and you have non-volatile memory and you have disk, you can integrate them as different tiers, and you can decide how the system should interact with these tiers, and you can also decide on a per node basis, this is something I haven't shown, on which particular storage class a certain node should preferably be allocated on. But the system is designed to embrace multiple technologies, current and future technologies.
Thank you.
All right, let's thank all the speakers, and that's the end of the session.